Hello everyone. In this short video, I will talk about the right hand thumb rule, then force implied by magnetic field on a current carrying conductor. Let us first talk about repulsion and attraction. How two magnetic fields interact to cause repulsive and attractive forces between two magnets or two magnetic fields. Whenever two magnetic fields interact, their pattern of interaction decides either they will attract each other or repel each other. Here I have two images. Here I have two bar magnets with their north poles facing each other. Now if we look at the section A and B of their field lines, we find that field lines appear to be parallel and pointing in same direction. Whenever field lines are parallel and pointing in same direction, they repel each other. So, in case of image 1, these two magnets will repel each other. Now, consider image 2. Here I have two magnets. The north pole of one magnet is facing the south pole of another magnet. Again, if we consider the section A and section B of their magnetic field lines, this is the interaction zone of these two field lines. If we consider the field lines in the interaction zone, we find that field lines appear to be parallel but pointing in opposite direction. Whenever field lines are parallel and in opposite direction, they attract each other. So these two magnets will attract each other. Now, coming to the next topic, right hand thumb rule in current carrying conductor. What is it used for? Consider this rolled up paper as a current carrying conductor. The direction of current is shown by the arrow. That means the current is traveling from bottom to top. Right hand thumb rule says that if we point our thumb in direction of current and curl our fingers around the conductor, then the direction of curling gives us the direction of magnetic field created by this conductor. So this conductor creates a magnetic field in the pattern of concentric circles around it, and the direction is decided by the right hand thumb rule. To represent the magnetic fields created by this conductor, I have this piece of paper which shows the concentric circles. So in this case, we have an anti-clockwise magnetic field. Now we will understand how concentric fields interact with each other and how they repel or attract each other. Consider this image. Here we have two conductors which are perpendicular to the plane of paper, and the direction of current is into the plane of paper. So, according to right hand thumb rule, both the conductors will create a magnetic field in clockwise direction. Clockwise direction, clockwise direction. The thumb is representing the direction of current. So, these two fields interact at this point. Consider this zone. Here we see that one field line is pointing downward and another is pointing upward. So field lines appear to be parallel at this zone, only at this zone. Of course, field lines are not parallel because they are concentric, but only at this zone field lines appear to be parallel and in opposite direction. So they will attract each other. This is the reason why transmission lines attract each other, because they are parallel and they also carry current in same direction. Now consider this image. Here again we have two conductors, both perpendicular to the plane of paper, In this case, current is coming out of the page, and in this case current is going into the page. So according to right hand thumb rule, thumb will indicate the direction of current and it will create an anti-clockwise field, and in this case thumb will point downward and it will create a clockwise field. Now again these two fields will interact at this point. Consider this zone. Here we see both are pointing upward, so the field line appear to be parallel and pointing in same direction. So this is a case of repulsion. These two field lines will repel each other. Now we will discuss the second topic of our discussion, which is the force applied by a magnetic field on a current carrying conductor. Here is an experimental setup. This is a horseshoe magnet and here is a conductor. The current is traveling from B to A, and this field is applying an inward force on this conductor. Practically this is a horseshoe magnet and the conductor is placed inside like this. So we will try to learn why the conductor is being pulled inside. Look at this image. The field lines of horseshoe magnet are somewhat like this, and field lines of this conductor are in anti-clockwise direction because the current is coming from inside out. So we will get an anti-clockwise magnetic field. Now look at the interaction zone of these two field lines. We can see the portion of field line appear to be parallel and pointing in opposite direction. Whenever they are parallel and pointing in opposite direction, they attract each other. So force of attraction will arise between these two field lines. That is the reason this conductor is being attracted inside the U-shaped horseshoe magnet. If we reverse the direction of current, the conductor will be pushed outside. There is also another method to decide in which direction the force will act. This is called the Fleming's left hand rule. According to Fleming's left hand rule, 3 fingers of our left hand stretched out like this can be used to determine the direction of force. In this rule, the forefinger represents the direction of field, middle finger represents the direction of current, and the thumb represents the direction of force. So let us apply Fleming's left hand rule in this case. So our forefinger will represent the direction of magnetic field. It is upward because north to south. Now the middle finger should represent the direction of current. The direction of current is from inside out. So now the middle finger is representing the direction of current. Now we can see that the thumb is automatically representing the direction of force, which is inward.